So far what we did is we have considered a basic negative clamper circuit under ideal conditions. Okay, we do not have any resistor, but if you take the practical clamper circuit, right, I showed some resistor across it. What for this resistor? Let us see this. Actually, what is the problem with the clamper circuit we have taken? If you take this clamper circuit, see, suppose I gave some input like 5 sine omega t. Then what is happening? The capacitor will charge up to 5 volts. Later the diode is off. So 0 less than t by 4, diode on. We know the whole story. So the capacitor is charging to 5 volts. Okay, here I am erasing. Next, for t greater than t by 4, after the first positive quarter cycle, diode is off. Once the diode is off, we know it acts as open circuit. Plus minus, the capacitor has charged up to 5 volts, and V input is like some 5 sine omega t, and V output is V input minus V capacitor, that is 5 sine omega t minus 5. Everything is fine. Now I remove the input. Once the power supply is off, then what happens? The equivalent circuit is anyway diode is off and the input is removed, so it is like short circuit only. And this is our circuit because V input is 0. Voltage source is 0. Under ideal conditions it is short circuit. Then what about the voltage across the capacitor? 5 volts only. Is there any path for the capacitor to discharge? No. I hope you get it. Now, right after, right, next again I would like to apply some input like 2 sine omega t. Is it not so? Next, if I apply some input, then the capacitor is unable to discharge, right? The capacitor cannot discharge and holds 5 volts only. Holds the 5 volts. Okay. Now I am applying an input, right, to the same circuit. Anyway, diode is under open circuit only. To this circuit, if my input is with the same condition, now I am applying the input. Instead of 0, I am giving here some 2 sine omega t. Then what happens? Here it is 5 volts and V output or VD, it is equal to V input minus V capacitor. It is 2 sine omega t minus 5. So what is VD maximum? VD maximum is equal to minus 3 volts, implies the diode does not conduct. And how about the output waveform? We expect and output is equal to V output is equal to 2 sine omega t minus 5 instead of 2 sine omega t minus 2. What do we expect? The moment you see a clamper, negative clamper, what do we expect? Output should be input minus peak amplitude of the input. 2 sine omega t minus 2. This is the expected output. But what you see? Only this. This is one issue we can see. Under ideal conditions, I'm speaking. Okay, so you can see some offset voltage across the capacitor. Initially, right, if it is 0 initial conditions, well, but in this case, what is happening? You can see non-zero initial conditions. Then how to overcome this? Earlier, I started with an analysis of 0 initial conditions. That's why we got the result 5 sine omega t minus 5. But now, right, with the same circuit, if I remove the input, I sub power switch off the power supply and again switch on and applied an input of amplitude 2 sin omega t, then what is the output? You expect 2 sin omega t minus 2, but you get 2 sin omega t minus 5 because the capacitor is unable to lose the voltage it has acquired in the previous transition. Okay, this is the problem. So how to overcome this? Yes, to overcome this, the practical clamper circuit I can write. A negative clamper. Let me write so. Just connect a resistor. Of course, practically once you are designing a system means whose output is given as input to some other system, that some other system itself acts as a load. You can even take that also. But right now system is connected as far as our present topic is concerned. So I am placing one resistor R and capacitor V input. Right. So what happens? Our input is 5 sin omega t only. Then over the interval 0 less than t less than t by 4, as usual, diode is on. Assume 0 initial conditions. Okay. Okay. Diode is on. And what is the equivalent circuit? This way. Here, diode forward resistance RF, R, C, input, output. Now, if you look at this combination, RF is very much small in comparison with R. We choose R to be large. Okay, resistor R is large. So RF parallel with R, its equivalent is RF only. RF parallel with R is approximately equal to RF. So the equivalent circuit now looks in the similar fashion. Even less than RF, strictly speaking. This is how the current flows and this is how the capacitor charges. So the circuit is same as that of the previous one only. Is it not so? So the capacitor rapidly charges towards input with a time constant RF into C. Okay, let me write the waveforms here also. Here, I'm just showing the waveforms. Input, V capacitor, V output. So, okay. So, now here what I can write, the capacitor rapidly charges towards input with time constant tau C is equal to RF into C. Okay, the capacitor is rapidly charging towards input. During that time, output is almost negligible. Or in the equation, V input is equal to V capacitor plus VD, and VD is negligible. So V capacitor is approximately equal to V input. As usual, the same story is repeating. So it is 5 volts at t is equal to t by 4, the capacitor voltage is slightly less than input voltage, the same story. Okay. And later for t greater than t by 4, the input tries to fall below 5 volts and the capacitor voltage tries to rise above, tries to reach 5 volts, which makes the diode to off. And for t greater than t by 4, for t greater than t by 4, once the diode is off, we know that all the story. I'm not writing all the steps again and again, right? We are well aware of it. Okay. Once the diode is off, then diode is acting as open circuit, but we have this R in parallel with the diode. Okay. This is our circuit. Now it looks like there is a path for the capacitor to discharge. Okay. So input is 5 sine omega t. And now it looks like there is a path for the capacitor to discharge. Okay, done. So it tries to discharge. But if I choose the time constant RC, what is the discharging time constant? It is RC. Okay, now the capacitor tries to discharge through R. Okay, it is trying to discharge. Capacitor is trying to discharge through the resistor. Okay, through the path. Okay, anyway, are trying to discharge with a time constant. Let me take so y through R. Right. So discharge with a time constant tau d, the discharging time constant is equal to RC. If that is the case, here it looks like the capacitor is discharging. But if I choose the time constant to be very large, if RC is far greater than t, where t is the time period of the input signal, then capacitor slowly discharges. See this. The capacitor then slowly discharges like this. Time constant. Okay. But meanwhile, what about the input? Right? The capacitor is trying to discharge like this. So it is almost like at 5 volts only, right? It is almost at 5 only. Okay, 5 to, right, because of the larger value of the time constant, it may come down up to 4.95 or 4. And what about V output? It is V in minus V capacitor. So the capacitor voltage is almost constant due to the larger time constant. The capacitor is unable to discharge. Meanwhile, what the input is doing? Input is varying sinusoidally and V output is equal to V in minus V capacitor. What about V output? It is almost constant, right? It tries to discharge, but what I did here, I have not chosen the time constant RC to be small. I choose it to be very large compared to the time period. As the time constant is very much large, the capacitor is discharging very slow, so that almost it appears like 5 volts only, right? The capacitor voltage almost appears like 5 volts. So that what is our output? Output is almost equal to V input minus V capacitor, that is 5 sin omega t minus 5. It also does not change its shape. This. Okay, because I hope you understand it. The capacitor, because of the larger time constant, the capacitor is unable to discharge fast. So it almost appears like 5 volts only, and hence the output is 5 sin omega t minus 1. Okay, this is the idea. And what is the general thing we took in laboratories? RC is greater than time period, means at least 10 times the time period we take. So generally what we take, RC is at least 10 times the time period. Okay, as far as the laboratory experiment is concerned, 10 times we take. So that you can see the output like this. And one more thing, okay, now I am removing the input. If I remove the input, what happens? Okay, suppose the input is removed. Then how about the circuit? Right here, the input is removed means, right, it is short circuit, and we have the diode like this and the resistor. And what about the voltage across the capacitor? 5 volts. Anyway, diode is off. So what is its equivalent circuit? Here we can take open, diode is open, and the resistor. Now the capacitor will very comfortably discharge. Through this resistor. Is it not so? Because here it is anyway short circuit. The path is completed here. Right? We have the path completed. Earlier, if you take without R, there is no path for the capacitor to discharge. Now the circuit is complete. Now path is complete, the capacitor discharges. Oh, sorry, reverse I should write. Sorry. What about the discharging path? This is our discharging path. Whatever the voltage the capacitor has, that will lose. So that we can see zero initial conditions. So once the capacitor is discharging, next if you apply input, what happens? That the capacitor slowly, once the input is removed, this is the equivalent circuit, the capacitor discharges with the time constant RC. It may take time, but capacitor will lose its voltage. The same thing is followed earlier, right? But it takes time, no doubt about it, but it takes time. Next time, so it discharges with time constant RC, and finally, the capacitor voltage approaches 0. Capacitor voltage is becoming 0. So what is the thing next? So that once you take the same clamper circuit, next if you apply from this case to, right, from this case to, if you apply some 2 sine omega t, then what happens? The same procedure. Now I can comfortably expect the output to be 2 sine omega t minus 2. Okay, the capacitor is now coming with 0 initial conditions. Why it is happening so? Because of the resistor we are connecting. The resistor during the discharge in the presence of 5 sin omega t is not influencing the output. But once the input is removed, that helps the capacitor to discharge completely, so that the capacitor voltage becomes 0. So that next time when you apply an input of 2 sin omega t, or something like that, a voltage which is less than the previous case, then it works properly as a negative clamper. Okay, this is the idea. Okay, and one more thing here, if you use this circuit, as I said, practical clamper circuit and all, right here 5 sin omega t, next I applied 2 sin omega t. If I give some 6 sin omega t, no issues, because it is more than, right here what did I write? If the input is, instead of 5 sin omega t, if it is 6 sin omega t, then 6 sin omega capacitor will charge up to 6 volts. There is a scope for diode to conduct, and the capacitor will charge up to 6, and output is equal to 6 sin omega t minus 6. That is possible. But if the input is less than 5 sin omega t, then diode never conducts, and there is no scope for the capacitor to charge further or discharge further. Okay, this is the idea. That's why I took here 2 sin omega t instead of some 6 sin omega t or 7 sin omega t, like that. If it is more than the 5 volts, diode will conduct and the capacitor will charge to that new peak. But if the peak amplitude of the input is less than the previous case, then it is difficult. Okay, keeping that in mind, all right, I did so. Okay, now once if I use this kind of circuit, there are no issues at all. This is what is called the practical clamper circuit. Okay, it's a negative clamper. Okay, this is done. What for this resistor? Next, this is unbiased, negative unbiased clamper. Next, biased clamper means I am using some reference voltage. If I use some reference voltage, what happens here? See, for time being, for better understanding, I am not using the resistor, but always there is a resistor in parallel with the diode. Okay, I am just taking this one. It is negative clamper with biased clamper. Or a biased negative clamper. Okay, negative biased means again, people will be thinking like it's not negative biasing, right? It's better to write it. Okay, a biased negative clamper. Okay, this is better. And the same input is some 5 sin omega t, and my reference is some 2 volts. Then what happens? Okay, if you take this, for the diode to conduct, the anode voltage should be greater than cathode voltage. Okay, so for that, if I take the waveforms and all, input has peak amplitude of 5 volts. Okay, V capacitor, V output. So when input is 0, then at this point at t is equal to 0, there is no possibility for diode to conduct, because anode voltage is, capacitor is anyway assuming 0 initial conditions, the capacitor voltage is 0, and means the capacitor acts as a short circuit, and anode voltage is 0 and cathode voltage is 2, diode does not conduct. Next, at some time t is equal to t1, 2 volts I am writing. So how long the diode does not conduct? As long as the input is less than 2 volts. So that means anode voltage is less than cathode voltage. Okay, so the capacitor simply acts as short circuit. There is up to 0 less than t less than t1, diode is off. and capacitor acts as short circuit. Okay, so what is our equivalent circuit? This one, diode is off and 2 volts reference voltage. Input, it is 5 sin omega t, and V output. What is V output? Output is equal to input. So whatever the shape you have for input, the same shape we can see at the output as well. It will be up rising up to 2 volts. Okay. At t is equal to T1, input is just exceeding 2 volts, means the anode voltage is greater than cathode voltage. Immediately the diode starts conducting. It is T by 4. I can take. Okay. So from T1 less than T by 4, the input is greater than 2 volts, so that the diode immediately conducts. Diode is on. Once the diode is on, then it acts as short circuit. So this is how the current will be flowing. So the capacitor starts charging with polarities plus minus, left to right. Okay. So the capacitor starts charging towards input with time constant RF into C. Ideally diode acts as short circuit, not at all an issue. So now what is the output equation? Then the capacitor will rapidly charge towards input with time constant RF into C. Okay. Then the capacitor is just following the shape of the input, right? So what about V capacitor? V capacitor output is equal to, it looks like output is equal to 2 volts from 0 to T by 4. I can take. So output is 2. What about V capacitor? It is V in minus V output. We can write. Okay. So V capacitor is equal to, it's not like V capacitor is equal to input. Earlier what happened? The capacitor voltage is equal to input because output was 0. But now output is 2 volts, and hence V capacitor is equal to V input minus 2. Means it is 5 sin omega t minus 2. I can write it. Only this is true only during the interval T1 to T by 4. Okay. At T is equal to T by 4, input is 5 volts and V capacitor is equal to 5 minus 2, 3 volts. The capacitor will charge up to only 3 volts. Is it not so? Okay. So the capacitor will charge up to, or I can say at T is equal to T by 4, input is 5 volts, and due to small delay, the capacitor voltage is, ideally it should be 3 volts, but slightly less than 3, I can say. Okay. Maybe 2.9. Okay. So at T is equal to T by 4, V input is reaching 5 volts, and due to small delay, and V capacitor is equal to 5 minus 2, it is equal to 3 volts. This is the expected value. But due to small delay, V capacitor is not exactly equal to 3 volts. It is something like 2.9 volts like this. Just slightly less. It's all for our understanding purpose only. Right? We don't know really exactly what value it is. Slightly less. So that, and for t greater than t by 4, the input just falls below 5 volts, maybe some 4.9 volt, and by that time the capacitor voltage reaches 3 volts, the expected value. So that VD is equal to, actually what is V output if you take so, V output is equal to voltage across the diode plus 2 volts. Is it not so? Here, if you take V output is equal to VD, voltage across the diode plus 2 volts. Okay. So, if I take the loop equation instead of writing VD directly for better understanding of students, I am taking one more step. V input is equal to voltage across the capacitor plus VD plus 2 volts. We know this scenario. Then what is VD? It is V in minus V capacitor minus 2. So V input, it is 4.9 and V capacitor is 3 minus 2. It is equal to minus 0.1 volt. Diode is experiencing some negative voltage. Is it not so? Implies the diode is off. Once the diode is off, what is our equivalent circuit? Simply the diode acts as open circuit, and this is 2 volts plus minus. The capacitor has charged up to 3 volts. V input and V output. So what is V output, friends? It is V input minus 3. It is just nothing but 5 sin omega t minus 3. Is it not so? Means, see, from here onwards, what happens? The diode is open. Okay, I'm not writing here VD. Earlier I wrote VD. Now I'm writing V output. Okay, V output I'm writing here. What is V output here? V input minus 5 sin omega t minus 3 I wrote it. Or as the diode is open, so whatever the variations you have in input, that can be shared by the capacitor and output. Okay, V input is equal to V capacitor plus V output, and the capacitor voltage is unable to change, then whatever the variations we have in input, all those variations can be seen across the output terminals. Means from this point to input is falling by 5 at this point. Okay, so input is falling by 5 volts from this peak to here. Just once the diode is off, just a point, the capacitor voltage remains constant. As the diode is off, the capacitor voltage can neither rise nor decrease. It holds constant. It is staying at 3 volts. Yes. Okay. Now, from this point to this point, you see, here the input voltage is input voltage is falling by 3 volts. By that time, the capacitor voltage falls up to, the capacitor voltage is 3. So the output voltage also falls by 3. So it is becoming 0. Okay. Further, from this point to this point, input is falling by 2. Output also falls by 2. Is it not so? So here to here, input falls by 5. And here to here, the output also falls by 5. Next, here to here, input falls by another 5. And the output also falls by another 5. Next, from this point to this point, this point to this point, input is rising by 5, output also rises by 5. Next, from this point to this point, this point to this point, right? Input is rising by another 5. Output also rises up to another 5 volts. Up to 2 volts only, right? And next it continues. And here, from this point to this point, input is falling by 5 and output also falls by 5, means to what level it will fall? It falls up to -3. 2 to -3. So the difference is 5. Okay. Again, -3 to, again input here falls by 5, means output also is falling by 5. So it falls up to -8 volts. Is it not so? Again here input is rising by 5, output also rises by 5. So it becomes -3. Here to here input rises by 5, output also rising by 5. So -3 to 2 it will rise. Again 2 to -3, -3 to -8, like this. This is how we can see. I hope you get it. Now this is the transient part. This is the transient part. So if you observe the output, it is like a 5 sine omega t signal appearing with respect to -3. Is it not so? In steady state, I can say 5 sine omega t is appearing with respect to -3. So I can say the steady state output. Next page I'm writing. In steady state, we output is equal to -3 plus 5 sine omega t. Okay. So instead of appearing with respect to -5 volts, the output is now appearing with respect to -3 volts. It is 2 volts and -8 volts. This is how we can see the response. I hope you get it. And we know that also, here I am writing, also V output is equal to Vd plus 3 volts. Is it not so? Okay, I wrote this statement earlier also. Vd plus 2, sorry, Vd plus 2, not 3. Which is also equal to -3 plus 5 sine omega t. Which means, what is your Vd, friends? 5 sine omega t minus 5. There is no change in Vd equation. Earlier, Vd and V output are one and the same, which is equal to 5 sine omega t minus 5. Is it not so? The diode voltage V output is like this, and Vd, the diode voltage, if you take so, it is always with respect to -5 volts only. Vd is like this only, but V output is Vd plus 2, means this Vd is minus 5 sine omega t, sorry, 5 sine omega t minus 5, for which 2 volts is added. That's it. Means, you know the output without this 2 volts. Without 2 volts, the output of the circuit is 5 sine omega t minus 5, for which you are adding 2, so that the overall output is 5 sine omega t minus 5 plus 2. That is the final conclusion. Okay. So what you can understand is here. See this, friends. So if I take the basic circuit, 5 sine omega t. Okay, and V capacitor is equal to V input peak, which is equal to 5 volts, and Vd and V output are one and the same, that is equal to 5 sine omega t minus 5. That's it. First point. Next case, what we are doing is, I am placing here a reference voltage of 2 volts. Then the input is 5 sine omega t. Then what about the Vd? Vd remains the same. Vd is 5 sine omega t minus 5 only, no doubt about it. But the output, if you take, output is equal to, or let me write V capacitor first, not an issue. What level the capacitor is charging in this case? V capacitor is equal to V in peak minus V reference. That is 5, V input peak is 5 minus V reference is 2. To this level, the output is, capacitor is charging. It is not V input peak. The capacitor will charge up to, V capacitor is equal to V peak. Please do remember this. V input peak minus V reference to that level. Okay. And what about V output? V output is equal to V in minus V capacitor. No doubt about it. If you take it, 5 sine omega t minus 3. Otherwise, also we can write it like Vd plus V reference. What is Vd? It is 5 sine omega t minus 5 plus V reference is 2. However you do, you get the result. I hope you understand it. This is the idea behind it. Okay. Blindly what you can take is, if you see the basic clamper circuit, output is equal to input minus peak amplitude of the input. Blindly we can write it. Now coming to the reference voltage, whenever you have reference voltage, whatever the output you are expecting, for that you need to add the reference voltage. Simply speaking, that's the final answer. Okay. So the basic circuit output we know, whenever you have some reference voltage, add this reference to the voltage you are expecting without any reference voltage. That is the final conclusion. And internal operation, etc., that's a different story. Those are all for our better understanding purpose. I hope you get the point. And we know how to write this output equation, right? 5 sine omega t minus 3. We know how to write this equation. And one more interesting point here, the reference voltage need not be positive. Okay, it can be negative also. And to what negative level you can raise and what positive level you can raise. Let us see. I am taking a case where the reference voltage is something like minus 3 volts, doesn't matter, or 4 volts you take, not an issue. V input and the capacitor V output. And to what level the capacitor will charge? Simply speaking, what is the output? V output is equal to Vd plus V reference. And what is Vd expected output? Vd is 5 sine omega t minus 5. And what is the reference voltage? Minus 4. Sorry, not minus 9. So the final answer is 5 sine omega t minus 9. That's the answer. Suppose they ask, what is V capacitor? V capacitor is equal to V input peak minus V reference. V input peak is 5 and V reference is minus 4. So 9 volts. The capacitor will charge up to 9 volts. No doubt about it. Okay. And if you want, you can try the transient response, how the things are. I'm directly writing the final result. Just like that, we can write this final answer. Okay, the next point. So negative reference voltage you can take like this, and positive reference means again, oh sorry, suppose I'm giving here 6 volts and input is 5 sin omega t. We output. What is the output of this particular case? See, what is there? So initially the diode is off, definitely, and it's open circuit. For the diode to conduct, the anode voltage should be greater than cathode voltage. But is there any scope for the anode voltage to go above cathode voltage? No. Okay. So 0 to T by 4 if you take, what is happening? Diode is off. Or V input peak is less than V reference. I can write here V input peak is equal to 5 volts, which is less than V reference, that is 6 volts. So there is no scope for diode to conduct. Diode never conducts. And capacitor cannot charge. So the capacitor simply acts as short circuit. Diode is open and it is 6 volts and 5 sin omega t. And what is our output, friends? It is simply equal to input, that is 5 sin omega t. There is no possibility of clamping at all. Output is equal to input in this case. When is it possible? Means when the reference voltage is greater than the peak amplitude of the input. Okay, this is the story. So these are all the possible cases with reference voltage. And more practical clamping circuit, how it appears. Anyway, I am writing here this way. R input 2 volts or V reference, something like that, input. Like this we can write. And one more thing we can see here, that right, reference voltage has an upper limit. No need to worry about the lower limit, but there is a restriction with respect to the upper limit, right? And with positive reference voltage, what we can do is we can place here, some GNR diode like this. Input. And what about the output here? V output is equal to, right, Vd plus Vz. Of course, there is a condition that input should be greater than the breakdown voltage of the generator. What is Vd? Vd is equal to Vm sin omega t minus Vm. I'm generalizing it. Instead of writing 5 sin omega t minus 5, I'm writing Vm sin omega t minus Vm plus Vz. Condition is Vm should be greater than Vz. Must and should. Otherwise, the circuit doesn't work. Instead of V reference, some reference voltage, I am placing here some GNR. I hope you all get the point. Okay. Unless the input is, right, if the input is less than the breakdown voltage of the GNR diode, the diode acts as open circuit. Once the input is greater than breakdown voltage of the GNR diode, then GNR diode undergoes breakdown and diode, almost ordinary diode, acts as short circuit. The capacitor will rapidly charge up to input minus Vz. And once the input falls below its peak amplitude, then the diode will be off and GNR diode comes out of breakdown, and output is equal to V input minus V capacitor, or Vm sin omega t minus Vm minus plus Vz. This is how we can take. Okay, this is the idea. Next, further we have to see if the diode is not ideal, how the output is. And what about the response if the input is square wave and all? We will see that next.